video, we will discuss about the following topics: fossils, absolute dating, and radiocarbon dating. Let us now start. Hope you'll enjoy!
All evidences of ancient life on Earth are termed fossils. The most common fossils are found in sedimentary rocks, where various processes work to preserve them for thousands, millions, or billions of years. The study of those processes of preservation is known as taphonomy.
What are fossils?
So now, what are fossils? Fossils are the preserved remains or traces of organisms. Fossils are very important for the determination of the possible age of formation of sedimentary rocks. So fossils provides us the best links to the previous history of life. And fossils, this includes our body fossils, casts, molds, trackways, feeding traces, and footprints.
And to acquire fossilization, there are some conditions that are required.
So, there are some conditions that require to permit fossilization. First, what is fossilization? Fossilization is a process of converting a organism into fossils. It is a process wherein the organic content of the fossils is replaced with a mineral substance in the presence of an organism. First, rapid burial. Rapid burial prevents the decomposition of the organisms. Without oxygen, the rate of decay of the organisms or the body of the fossils becomes slow. Second, protective cover or medium. A protective cover or medium will prevent the attack of organisms living on dead organisms and prevent the air and moisture from building up. Third, possession of hard parts or durable tissues. Soft tissues, organs, or flesh usually disintegrates. Why? Because the most stuff of the organisms like body organs and deep tissues decomposes way too fast to be fossilized, while the bones, teeth or shells and other hard parts of the organisms or fossils will most likely be preserved during the process of fossilization.
There are different types of fossilization depending on the preservation and medium involved. However, there are three most common types of fossilization.
And there are three different types of fossilization. The first one is preservation without alteration. The second one is preservation with alteration. And the last one is ichnofossils or trace fossils. Let's go first to the first type, preservation without alteration. Preservation without alteration is a type of fossilization wherein no major changes or modification of the chemistry occurred. This type of fossilization provides the excellent window for studying the ancient life because most of the organic molecules are still there. Now, the second type, preservation with alteration. Most fossilization proceeds with altering the chemical composition of organic remains. The subtypes of preservation are dependent on the process involved. Under the preservation with alteration, there are three common subtypes of preservation with alteration. The first type is petrification, or known as permineralization. The second type is recrystallization, and the third type is carbonization. Now let's go first to the first type, petrification. Probably the most popular method of preservation with alteration. Petrification is the replacement of porous woody material with minerals. The original wood components are already replaced by materials such as silica living in rock, image, and elements. The second type is recrystallization. Recrystallization, shells of organisms made from the calcium carbonate, aragonite are unstable at near surface conditions. When the organism dies, the aragonite recrystallizes, forming the much more stable polymorph or calcite. And the third most common subtypes of preservation with alteration is carbonization. Carbonization, soft tissues of organisms can be preserved through the process of carbonization. This process leaves the carbon component of the remains as black films embedded in sediments. The third type of fossilization is ichnofossils or trace fossils. The success percentage of organic remains is very small. Most organic remains are destroyed early through process of decay and erosion. There are, however, cases where remains are not the usual body fossils but are traces of the organisms itself. These types of fossils are called ichnofossils. Ichnofossils include molds, casts, bureaus, coprolites, and gastroliths.
Absolute dating.
Now, let's talk about absolute dating. First, what is absolute dating? Absolute dating provides a numerical age or range, in contrast with relative dating. Relative dating, which places events in order without any measure of the age between events. Now, first let us contrast absolute dating and relative dating.
What is the difference between absolute and relative dating?
First, relative dating determines only whether an object is in order from younger to older, just like that. For example, I'm younger than him, he's older than me, or she's younger than him, just like that. Remember that relative dating does not give an actual or exact age. It just put objects in order from oldest to youngest. Sedimentary rock. Now, sedimentary rock is a rock that forms from the fragments of other types of rock, just like metamorphic or igneous rock. Sedimentary rocks are the most useful rock for relative dating. Because it forms when sediment is deposited and liquefied or hardened. Now, both relative and absolute dating are used to determine an age of an object. But contrast with relative dating, absolute dating gives the exact, fixed, or actual age of an object. Now, you are seeing a picture and the difference about relative dating and absolute dating. On the left side of the picture, you can see on the label whether a layer is older or younger than the other. While on the right side, you can see an exact age of layers. Now, law of superposition. Law of superposition states that older rock layers are often below the younger rock layers, or younger rock layers are often above older rock layers. In historical geology, the primary methods of absolute dating involve using the radioactive dating. Radioactive decay of elements trapped in rocks or minerals. What is radioactive decay? Radioactive decay occurs when unstable atoms break down to a more stable form. The rate at which these atoms break down can be used to date rocks or fossils. Radioactive isotopes are variants of the same element but with different mass number. Because of the extra subatomic particles in the isotope, the atom spontaneously breaks apart, or does the decay, which produces a more stable daughter product. This transformation of parent isotope to stable product varies from element to element and is often measured in terms of half-lives or half-life. Half-life is the length of time that will transform half of the parent isotope to its daughter product. To simply put in analogy, given 100 grams of the radioactive parent X, the half-life is simple. The time required for 50 grams of parent X to convert into daughter Y.
Radiocarbon dating.
Good day everyone. I'm here in front to tackle about radiocarbon dating. First, who developed radiocarbon dating? His name is Willard Libby. So, who is Willard Libby? He is an American physical chemist, led a team of scientists in the post-World War II era to develop a method that measures radiocarbon activity. He is credited to be the first scientist to suggest that the unstable carbon isotope called radiocarbon or the carbon-14 might exist in living matter. Mr. Libby and his team of scientists were able to publish a paper summarizing the first detection of radiocarbon in an organic sample. So, it was also Mr. Libby who first measured radiocarbon's rate of decay and established 5,568 years as the first half-life. In 1960, Mr. Libby was awarded the Nobel Prize in Chemistry in recognition of his efforts to develop radiocarbon dating. So what is carbon-14? Carbon-14 is a weakly radioactive isotope of a carbon, also known as radiocarbon. It is an isotopic chronometer. Radiocarbon dating is only applicable in organic and some inorganic material. Radiocarbon dating is not applicable on all metals. So, radiocarbon dating labs use oxalic 1 and oxalic 2 as modern standards. Radiocarbon measurement are reported as conventional radiocarbon age. The impact of the radiocarbon dating technique on modern man has made it one of the most significant discoveries of the 20th century. No other scientific method has managed to revolutionize man's understanding not only of his present but also events that already happened thousands of years ago. Basic principles of carbon dating. Radiocarbon, or the carbon-14, is an isotope of the element carbon that is unstable and weakly radioactive. The stable isotopes are carbon-12 and carbon-13. Carbon-14 is continually being formed in the upper atmosphere of cosmic rays that the sun releases. On the nitrogen 14 that's being formed, it will mix in the air and it is rapidly oxidized in the air to form the carbon dioxide that the plants and animals inhale. Plants and animals assimilate carbon-14 from carbon dioxide throughout their entire lifetimes. When they die, they stop exchanging carbon with the biosphere and the carbon-14 content then starts to decrease at the rate determined by the law of radioactive decay.
Let's say you have a cute little Compsognathus dinosaur who eats a toxic plant and dies at the edge of a lake. Now, that Compsognathus skeleton is destined for destruction very soon. The scavengers are coming and so are the insects, bacteria, and weather fluctuations that will turn him into dust in no time. But look, all of a sudden, his body falls into the lake. It sinks to the bottom and now it's completely submerged. It's safe from the scavengers, the beetles, and bacteria. It's safe from the weather because temperatures are fairly constant underwater. Maybe a few fish eat the meat of his bones, but nobody carries his arms and legs away. Within a year, his body gets covered by all the silt and sediment accumulating on the lake bed.
There are many ways for paleontologists to guess how old a dinosaur bone is. One way is called stratigraphy. This means that we study how deeply a fossil is buried underground. Layers of rock are formed over millions of years. New layers are formed on top of old layers. So one way to guess a bone's age is to see which layer of rock it was in when it was found. The deeper the rock, the older the fossil. This isn't always very easy. The Earth is moving all the time. Old layers of rock are pushed to the surface, and new layers are formed when volcanoes erupt. Another way to find out a fossil's age is called radioisotope dating. This is the best way to find out how old a fossil is, but the fossil must be made out of certain kinds of rocks. Rocks like uranium-235 decay very slowly over time. This means that over many, many years, uranium-235 changes into another kind of rock called lead-207. It changes very slowly, at the same speed, no matter how old it is. The rate at which it changes is called its half-life. For example, uranium-235 has a half-life of over 700 million years. That means that it takes 700 million years for uranium-235 to turn into lead-207. So if paleontologists find a fossil, the first thing they will do is find out whether there is any uranium-235 in it. They will look at it very carefully to see whether it is turning into lead-207. If it is halfway changed, or mostly changed, or only starting to change, this will give them a good idea of how old the fossil is. Many times paleontologists never know exactly how old a fossil is. Usually they guess its range, or span of time. A good way of guessing the range is to look at the layers of rock that were formed by volcanoes. It's easier to guess the age of volcanic rock, because it's brand new rock from the moment that it's spit onto the Earth's surface. When a volcano spits out lava, it creates new rock. New rocks have almost no argon gas in them. As the rock gets older, the argon gas is released. The more argon gas a rock has, the older it is. Imagine that a volcano erupted 80 million years ago and spread a layer of volcanic rock over the Earth. Then imagine that a triceratops lived and died right on top of this layer. It was buried in the ground and became a fossil. And then, 10 million years later, another volcano blew a layer of rock on top of the buried skeleton. If the first layer of rock was 80 million years old and the second layer was 70 million years old, paleontologists can guess that the Triceratops skeleton was between 70 and 80 million years old. Finally, paleontologists can use what they call index fossils. These are fossils belonging to creatures that lived during a certain time period, and they are found next to other fossils. Let's say that we find the fossilized remains of a jellyfish. Since jellyfish are one of the oldest kinds of life on Earth and are still alive today, it will be very difficult to guess how old it is if we found it all by itself. But let's say that we find this jellyfish next to the fossil of a trilobite. We know that trilobites lived during the Paleozoic era, between 2,500 and 250 million years ago. So that means that the jellyfish would have lived at the same time. Because we are using the trilobite fossil to guess the age of the other fossil, the trilobite is our index fossil.
how do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.